Hello, everyone. I'm Hajishirzi from UW and AI2. In this talk, I will present some recent work in my lab in building general purpose and robust language and vision models. Vast amount of textual and visual data are available in many different formats and styles. As a result, the problem of understanding and reasoning about these different forms of data is really an important problem. Usually, the progress in understanding and reasoning, both in language and vision, is being measured with some sort of external applications, such as question answering and fact checking in NLP or object classification in computer vision. Usually, the goal in all these applications is to build an AI model that can map an input X to an output Y that is defined according to the task at hand. The current paradigm in AI is usually as follows. The pre-training stage, where models are designed to pre-train deep representations from unlabeled textual or visual data. For example, in NLP, we try to jointly condition on both left and right context in a piece of text. Then data sets or dataset construction, where the goal is to curate large-scale data sets for many NLP tasks or vision tasks. For example, in question answering alone, we have seen many data sets in the past few years. Then the fine-tuning stage, where the goal is to build task-specific models to fine-tune pre-trained representations over those curated data sets. For example, for the task of question answering, the input question and the context are encoded using pre-trained language models where we obtain text representations. Then, given the annotated data sets, the task-specific layers are trained. For example, the goal would be to extract a phrase that can answer the question. And finally, evaluation, where we're going to do data-set-specific evaluations for all those models. With this paradigm, we have observed great progress in building specialized or task-specific models. For instance, we have models with excellent performance on sentiment analysis, question answering, and machine translation. However, these models usually cannot generalize across tasks. How can we build models that can work well across many NLP tasks? For example, if we could multitask, if we could do some sort of multitask training and build general NLP models, can we say now they can generalize to an unseen task such as negotiation and strategy detection? This is really hard, mainly because the models don't know what that new task would be, and when they don't know the definition. Now let's move on to computer vision. And let me give you a quick history on vision models. We've had great progress in making specialized models for different computer vision tasks. These models often used closed vocabulary for different known object categories. More recently, we've seen great progress in building general purpose vision models, thanks to the open vocabulary models that use language models to encode many object classes. These models are trained on hundreds of millions or even billions of image caption pairs and show great performance even in zero-shot setting, as you can see here. Importantly, these zero-shot models are robust to natural distribution shifts. This figure, for example, compares the robustness results of ResNet 101 versus CLIP zero-shot models across different natural distribution shifts. And as you can see, CLIP zero-shot model is doing much better. Still, there are large performance gaps in many other data sets. For instance, In MNIST, the performance is even worse than logistic regression. Here, we like to build models that fix these issues. We want them to have high accuracy on a large collection of tasks. We want them to use low computational cost, especially at this stage of fine-tuning. Also, at the same time, we don't want to lose performance on original models. Each of zero-shot models, pre-training from scratch, or fine-tuning would lose at least one of these features. Here, in my lab, we've introduced wise fine-tuning method, which I'm going to talk in this presentation, that would satisfy all these requirements. Okay, so our goal in my lab, both at UW and at AI2, is to challenge the current AI paradigms. We like to design models that are general purpose and robust in both language and vision domains. In this talk, I will present some recent work on how to build NLP and vision models that are robust to distribution shifts, and also they can generalize to new tasks. First, I would present our work on building a unified multitask learning model that can answer different types of questions in natural language processing. Second, I show how we use meta training to learn new tasks only from a few examples. Third, I would present our recent benchmark that evaluate task generalization across more than 1,600 NLP tasks, given some loose descriptions about their definitions. And then finally, I would present our work in building robust fine-tuning and patching models in computer vision. Okay, our first work. Our first work is to build a unified question answering model led by Daniel and Saiwan, which was published in 2020. We have observed a surge of new data sets across many tasks, including question answering in NLP. Here I'm just listing a few of those. These data sets are usually designed to evaluate different reasoning challenges under different types of contexts. And they are usually designed across different formats, such as multiple choice, Boolean, extractive, and abstractive. Here, we argue that there is an overlap between underlying reasoning abilities of these type of question answering tasks. And one can benefit from mixing all these question answering formats. In particular, we introduce unified QA that uses multitask learning to build a general purpose QA system. It sits in between pre-training and fine-tuning stages. It basically unifies the input-output formats for many different question answering data sets and map all of them into sequence-to-sequence text formats. And then it uses multitask learning to train the model. So I'm avoiding going into more details for this work. Here are our results. Dark blue shows the unified QA results and light blue shows the previous models. First, we show that our unified QA model performs almost as good as individual and specialized models targeted to each data set. In some cases, unified QA even performs better than the single data set expert. On average, unified QA clearly outperforms the ensemble over all these data sets and task-specific systems. Importantly, unified QA shows really promising results in out-of-domain distribution data sets. Here, we compare our unified QA result with previous best models when the data set is completely unseen for unified QA. Okay, in summary, we introduced unified QA, which opened up several future progress in this direction. Particularly, it is generalizable and achieves state-of-the-art results in new benchmarks. Also, other researchers have shown that similar method can be applied on other settings, for example, in few-shot learning. Also, it has inspired future work in using similar type of multitask learning and building unified model, for example, in common sense reasoning. Okay, so these results are great. Now, we want to show our newest work, which is how we can use meta training to be able to generalize beyond one specific task. Okay, here I'm excited to present our work. We call it meta in context learning, which is a new meta training approach for better in context learning. The key idea is to train the language model on a really large collection of meta training tasks using an in-context learning objective, and then test it in frozen and unseen tasks. Before we begin, let me first describe what is in-context learning. In-context learning is an approach that learns a new task at inference with no gradient updates. First, suppose we have K examples as training data. You concatenate all of them and then append it to the text input and then pass it to a language model and then let the language model to predict the next token. The intuition is that the language model is hopefully able to capture patterns in the given context, figuring out what the task is and make a prediction accordingly. Okay, for example, here we've done sentiment for the task of financial news. In principle, this can be done on any downstream tasks without updating the model parameters. For example, here we can expand the same idea and the same approach for topic classification on news. This is very attractive, but following work or kind of previous work has shown that this is highly unstable and has high variance. This was first introduced by the GPT-3 paper and has been advanced in many different dimensions. And then most of these models basically use the pre-training language model as it is. But now the question is, can we even make more benefit, get more benefit from this type of in-context learning? Or basically, can we meta-train the model to be a better in-context learner? More specifically, this is what we wonder. If we can meta-train the language model on a really large collection of downstream tasks in the in-context learning setup, can we meta-train it and then learn a new task given some examples that we have observed from similar tasks before? Okay, basically here is the idea. At the meta-training stage, the model, which is fully trainable, would see a few examples from related tasks. And then at inference, we would look at an unseen task and would see if we can predict the correct label. Okay. So this is the core idea. Let me walk you through more details. Meta ICL consists of two stages, the meta training stage and the inference stage. At the meta training time, the model has access to a large collection of meta training tasks, where each is paired with large labeled data. For each iteration, the model will pick one task, like AG News. Then it would look at a few examples from that task, or in particular, we're going to look at K+1 examples, where they are all passed to the language model, where The goal now is to predict the K+1's label, okay? Or basically all K examples will be concatenated to the K+1's input, and we want to predict the K+1's label, okay? Where this K+1's label would act as a test example, and the others will all act as training examples. At inference time, we have a new task. We call it a target task. We have the text input or the test input. Now, again, we have K examples, but now our instances are very similar to what we had trained the model on. Then the model will take this input and predict what the output Y is. But remember, now the language model is frozen. This is the very basic idea of meta-ICL, but then in a previous work, we have found that using a noisy channel approach by simply flipping X and Y leads to better performance. So we use that approach here as well and propose a model called channel meta-ICL. Everything is the same. Basically, we flipped X and Y. Now, let me move on to experiments. We included larger scale experiments with 142 data sets in total and 7 different settings for meta training and target splits. In this presentation, I will focus on the main setup where we take the data set with more than 10K training instances for meta training and the rest as tests. We think this is the most practical and realistic setting because we are likely to want to use high resources for training. We have a large collection of tasks, including question answering, text classification, and so on for our training and inference. Okay. I will first show results of our baselines. The first set of baselines are raw language models that are not meta-trained. The first 3 baselines are zero-shot methods, okay, that do not use any training data. And the next 3 bars are some sort of in-context learning that they would use the few examples. As expected, in-context learning overall is better. Next, we tried a baseline called multitask zero-shot that we took it from previous work. This model is trained on exactly same meta training tasks, but without in-context learning objective. We found that this method is not very competitive. This is likely because the model has no way to learn what the task is at inference time. Finally, here are our results for meta-ICL and channel meta-ICL. We find that each model outperforms its raw language model counterpart by a significant margin, because the argument is now we have trained the model to learn the task from a few examples. And at the end, channel meta-ICL achieves the best performance. Also, we evaluated models with different parameter sizes, showing that our method, meta-ICL, with 774 million parameters, outperformed the GPT-3 model, which uses 755 billion parameters. Finally, if we also add instructions to describe the task, we see more improvements. The orange line or the orange bars are the models where they also see instructions. In summary, you have to choose one instructions or the K-shot data, and we basically show that the combination is actually the best. Okay, so this basically leads to the next part of my talk, which is developing a benchmark to evaluate cross-task generalization for many NLP tasks, given the instructions and also a few examples. We call it natural instructions. Natural instructions is a really large scale kind of data set led by Zhang, Swarup, and Daniel. and a lot of other collaborators. Okay, let's look at this example. Person X yelled at person Y because blank was so upset about the news. When we show this to a person, what do? If we ask them, answer this fill in the blank question, they would successfully do that, right? They would say it's person X. We might ask the human to do something else, modify this fill in the blank question on persons, okay? And now they would change it, like person X comforted person Y because blank was so upset. Okay, humans can do it because basically we can give them the same context, ask them to do different things. They are great in these type of things, right? And we have an evidence because these were instructions to collect the Mino Grande data set. Now, our question is, can we have AI algorithms do that? Basically, what we want is, we want to have a model which is potentially trained on a large collection of NLP tasks. But now we want to have a task definition and also a few examples. Describe what the task of negotiation and strategy detection is. Then we like to be able to build an AI model that takes the other tasks as input in the training stage, look at the task definition, and then solve this new task. We constructed natural instructions data set that consists of more than 1,600 tasks in NLP over 76 broad categories, such as sentiment classification, dialogue generation, grammar error detection, and so on. This data is collected by 88 volunteers who are NLP practitioners who responded to our call for data collection, and they all collaborated via our GitHub repository. All these instructions are peer-reviewed, so we make sure that they are high quality. We have designed and unified the schema for instructions. In particular, we have defined minimal tasks by decomposing long instructions into single-step tasks. And we define this schema that consists of instructions, plus a list of positive examples, plus a list of negative examples, and then we have our instances. The positive and negative examples would show the annotators or the model how the task should be or should not be. This was our instruction goal. We wanted our instructions to be sufficient to define the task for an average human reader. And this is how we've collected instructions from our NLP practitioners. Then once the data is collected, for each of these tasks, like textual entailment, we have all the instances and some descriptions of how the task would be done. Then we set aside some of these tasks, in particular about 119 tasks for test. They are spread across 12 categories, 12 diverse categories. We use the rest of the tasks for training that includes more than 750 tasks across 64 categories. And we won't have overlap between the training and test splits. We train our model, we call it TK Instruct because it consists of a model that is trained in the in-context setup consisting of K examples and instructions. And this is trained on all our training data and in being evaluated on the test categories. Here are the results across different task categories. First, trivial baselines, blue and orange bars, show low performance, which is good news. Second, the multitask zero-shot model called T0 that does not use instructions show low performance. Then we compare our model, our TK Instruct model, which is trained on our training data, the purple bar, showing more like higher performance compared to all the baselines. At the same time, it shows performance on bar with GPT-3, which is the red bars, where GPT-3 instruct basically uses 175 billion parameters, whereas our model uses 3 billion parameters. Finally, the current models are still far behind the specialized model compared the performances compared to the dashed lines. This figure compares the accuracy in terms of the Rouge score versus the number of training tasks. This is important and interesting to observe that adding more tasks to the training data helps increasing the performance. As a sanity check, instead of kind of diversifying the tasks, we just added more training instances and we saw that the performance plateaus. We don't see any more gain. So it shows that the diversity of tasks enable the model to follow and understand instructions better. Here is our demo. You should be able to use our demo online. This would show things like this. We would ask the model to given a phrase, try to compose them into a long story, and the model does something like this. We expected the model to have Zhang Wang, Oranazioni, Bitcoin, and so on, and it comes this story. Also, we have a demo for our few-shot learning model using the channel meta ICL approach. Again, I encourage you to go and check out that demo. Okay, so now let's move on to the last part of my talk about how we learn to do robust fine-tuning and patching in computer vision. In particular, I will introduce our weight space fine-tuning approach. This is the work led by Gabriel, Mitch, and us. Our weight space or wise fine-tuning approach, we call it a better model for transfer learning. We introduce our weight space ensemble fine-tuning method that is effective in transfer learning. And in particular, we show that it is robust to distribution shift, and it's also robust to task shift. Let's see what I mean by being robust to distribution shift. Basically, the goal is we would like to train the model on ImageNet, and we would like to evaluate it on data sets that show some sort of natural distribution shift. Here is our proposed solution. We call it weight space ensemble that has two simple steps. First, we fine-tune a model called θ0 on a target task and obtain θ1. Then we interpolate between the weights of these models, which are before and after fine-tuning. The attractive feature of our wise fine-tune model is that it does not require any additional compute over standard fine-tuning. Let's show this pictorially. We use clip. Zero-shot clip is robust. When we fine-tune the clip model, it achieves high accuracy over ImageNet, but it is definitely less robust. Look at the drop in robustness accuracy. Wise fine-tune proposes to interpolate the weights between zero-shot clip and fine-tune clip using an alpha parameter. The results show this curve that is both robust and has high in-domain performance. Look at the top part. Overall, we can basically fine-tune alpha or tune alpha in our development set, but our experiments show that we can even observe great performance gains for alpha being 0.5. Here are the results. We observe significant performance gains in different out-of-distribution domain shifts. When we compare it to standard fine-tuned models, we have observed the highest improvement in the ImageNet A data set for the distribution shift. Now let's move on to a more complex setup where we want to see how to build models that are robust across tasks. In particular, what we want is to have a model that achieves high accuracy across many different tasks. We call this patching. Patching has an ambitious goal. The goal is to expand the set of tasks that the model supports with really high accuracy. Basically, what we want is that anyone that uses this model should see some improvements. Again, our solution is white space ensemble. Let's look at this figure. This figure shows MNIST accuracy versus ImageNet accuracy of vision transformers at different scales. Zero-shot models have high accuracy on ImageNet, but their performance is usually low on MNIST. On the other hand, the fine-tuned model have high accuracy on MNIST, which we call it our patching task, but it has low accuracy on ImageNet. Our wise fine-tuning comes to the rescue. Basically, it would resolve this problem. We would argue that this weight interpolation gives us the best of both worlds. Look at the results on this figure. In particular, at the fine-tuning stage, we fine-tune an open vocabulary model without any task-specific head. The model basically uses the text encoder and an image encoder. Here are the results. It shows high performance gains across many different types of transfer across different data sets, like CARS, Eurosat, MNIST, the Sun 397, all these data sets. We see different performance gains, but we do not lose accuracy on the original task. The accuracy drop or the performance drop is basically less than 1%. Importantly, we have observed better performance gains for larger scale models. This figure shows the accuracy distance to optimal versus different model sizes. And then it's been the dark purple shows it's being averaged over multiple transfers. And as you see, in larger scale models, this accuracy distance to optimal is actually kind of really minimal. Okay, so before what I showed was how we did patching over a single task. Now I want to show how we could do patching on multiple tasks at the same time. Okay, we've also experimented with this patching on multiple tasks, and we've used 3 different approaches. Parallel patching, where the idea is we're going to fine-tune on each task and then interpolate. Sequential patching, where we're going to patch one task at a time in the sequence. And then joint patching, which is merge all tasks into a larger one and then patch. So the limitation of joint patching is that we need to know the list of tasks that we want to expand at the training time. But the other 2, they can come one by one. Okay. This graph looks a little bit complicated, but it actually shows accuracy over different target tasks, okay, using different approaches. The light blue or the blue curve basically shows the accuracy of independently patching over each of those tasks. So that is kind of the goal we try to achieve. These are the specialized models for those tasks. The green, red, and purple basically show our 3 different strategies for multitask patching. And then the darker blue is the unpatched model. So the dark blue obviously has the lowest accuracy on these tasks. It's just like high in one of them, basically ImageNet. And interestingly, these results show that our joint patching approach, the purple line, basically is equivalent to independently patching on all of those, or basically build a specialized model. Okay, it only is 0.5% of using all those 10 specialized models. Okay, this is great. We introduced wise fine-tuning, which satisfies all these features that we were looking for. It is effective. It has a high accuracy on target tests. It is efficient. It doesn't have any additional computational cost compared to a regular fine-tuning model. And it doesn't have any side effect, like we do not lose accuracy on the initial tasks or in original tasks. Okay, so what is next? Basically, this is where we are trying to make more improvements. Our goal is to build general purpose NLP and vision models. Our kind of aspirations are around having robust models, where at the same time we want them to be efficient. We like to make emphasis on modeling, evaluation, data and analysis, and we also like to be engaged with engineering to update and have better kind of engineering platform. So all these four components are really important and necessary to see how these different proposed models work. For example, the analysis play an important role that would tell us what are the next series of models that would be more general purpose and more robust. Would it be collecting more data? Would it be larger scale data? Or would it be a kind of a different approach, like integrating symbolic and neural models? We also would like to be able to focus on tasks that or models that can transfer to other languages or other modalities. Okay, thank you.